Now we have one more session on multi-objective optimization by Dr. Devadula Srinivas from IIT Madras. Excuse me, sir. Sir, excuse me. Sir still has not joined.
Uh, Dear participants, tomorrow we are going to conclude this FD program. The feedback form will be posted tomorrow sessions. Yeah. Just now, Dr. Srinivas joined. Now I request Dr. Sri Reddy sir to welcome the guest. Welcome Srinivas. Welcome Dr. Srinivas. You are mute. You just unmute your mic. Srinivas. Yeah.
Yeah, thank you, Professor Vikram.
Hello, Srinivas.
Yeah, I could hear you. Hello. Yes. Am I audible? Yes. So thank you, sir. So good evening, everyone. I'm sure all of you are tired. In fact, I am also tired. Continuously from morning onwards, we have some of the other activities. So, but to make it a little bit interesting, I'm not presenting many slides. In fact, no slides. I want this session to be more communicative, so that we all will enjoy this session. First of all, my name is Srinivas. I am from Department of Mechanical Engineering, specifically from Manufacturing Engineering section, IIT Madras. I'm associate professor at Department of Mechanical Engineering, and yeah, the theme of this talk is AI and ML. Now I'm going to present something related to multi-objective optimization. So all of you might get some doubt how AI and ML is related to optimization. Yeah, so that we will discuss. And for the last 5 days, you might be hearing some presentations from multiple members on artificial intelligence and machine learning. So I don't think I need to give any introduction about that. So, by this time, you know very well what is AI and ML. So it is... So as a layman, let us discuss, why do we need AI and ML? Is it something, a magic? At first look, it looks like that, because it can predict share values, and it can predict process parameters for machining process. Whatever we feel, something complex or something difficult, these AI and ML techniques could do that. Now, recently you have seen ChatGPT, so which is giving answers for most of the things, if not 100% accurate, but at this preliminary stage, it is impressive. So we are very much overwhelmed by its performance. But how is it doing? That is the question. So we are using A and ML approaches there, multiple advanced algorithms, deep learning algorithms, many things we are using there, and we are getting the output. But now the question is, how are they doing? That is the question. Is it something like magic, or someone is there behind, or what exactly it is doing? Before going to answer that, let us see what is hacking. Some of our emails gets hacked. Some of the bank sites, some of the government organization sites gets hacked. So let us try to understand the idea behind that. What is hacking? That means somebody is taking control over our computer or our servers. How are they taking control over it? Because we are not giving our password, we are not giving our computer information, but still they are taking over your computer, right? So they're asking some money to release your computer, because you will be having all your data. Whether most of us, we don't take backup, so we badly need our computer back, control of the computer back. And nowadays, you know that we are too much dependent on these digital systems, fortunately or unfortunately. Of course, it is doing good to us, but however, if something goes wrong, we are helpless. In olden days, if you ask 17 multiplied by 16, all of us, we could tell immediately. But now, if you ask kids, most of them, they will not be able to tell, because whatever they want, they are getting on Google, on internet, on what we say, the small tabs. So they need not remember, or they need not by heart, they need not practice tables. That is one thing. So on the other hand, definitely it is making our life easier. For example, if you want to book some ticket, you need not. We used to go and stand in the lines before railway station from morning onwards. But now you need not do that. You can book a ticket from home without stepping out. So that is the benefit. So now let us go back to our hacking problem. Someone is hacking your computer without getting the information from you, or without getting a PIN number or password, but still they are hacking. That means there is some trick. What is that? That is, they know how a system works. They know how to build a website. They know how to operate a website. Right. So you are writing for SBI, or let us not take the names, for some bank. That is, after all, a website, right? And it stays on a server. So in your electronics or computer science or electrical engineering, or even now in core branches like mechanical or civil engineering also, we are teaching how to develop a website and how to give passwords and how to first of all, we are teaching them in straight way, but people need not think in a straight way, right? So if you say how to develop a website, they can do the reverse engineering and then they can hack the website. That means how to develop the website, that flow chart or that training, if you have, it is very easy to do the reverse engineering, right? So that means you need to understand the basic mechanism of developing a website. Once you know that, then it is very easy to crack, because after all, it is a program. It is a program written by some of us. Some of our students have written that program. So we taught those programs to them. So all of us know how to develop a website. So then the next step is how to crack that. Obviously, we know how it works. That means we can crack that. It is as simple as that. So why I'm giving this example? We do not want to crack any website, but or hack any website, but the essence we want to understand. What is that essence? How a system works, how chat GPT works, or how a model works, how a computer works. If you know that, then the next step is very easy. That means the mechanism is very, very important. Now, till now, most of the ML and AI algorithms, we are using them. We go to Python library, or we go to MATLAB. In MATLAB toolbox, we take it and then we implement them. So we do not really know, or we do not really try to understand how these algorithms are written, or how they are working. What is the working principle, right? So the other side of the coin we are exploring, that is how to use these machine learning algorithms or AI approaches. We are only using them. For example, if you want to develop a fuzzy logic model or neural networks model or a clustering model or something, whatever you want to do, those functions were already written in Python and MATLAB or C language or C sharp, multiple language or Java. In these languages, those functions are already developed. We are only using those functions for our application. For example, it is a machine tools or machining process or stock market prediction or weather prediction, whatever it is. So for that specific problem, we are using already the developed tools. Okay. So that is most of AL and ML, AI and ML algorithms are used in that way. But in this lecture, I'll try to understand the other side of the coin. What is that? How these algorithms work, how these systems work. Till this point, are there any questions? Please be communicative so that we can make this interaction more interesting.
No, sir, no question.
Yeah. So once again, I'm repeating the point. There are two sides of the coin. One, using the existing approaches, AI or ML, using them. For that, you need not understand how they work. Right. The second part is we are trying to understand how these algorithms are working so that tomorrow you can develop better algorithms. For example, now if you see Chat GPT, it is not able to give satisfactory solutions or answers for some of the questions because they are not very well developed yet. Still, they are in preliminary stage. If you know how this Chat GPT is working, immediately you get some 100 ideas. Oh, why not we do this way? At present, it is working this way. You are using this algorithm. That is the reason its performance is inferior. But you can do this way, or why not we do this way so that we can improve the performance. Right. So that is bringing novelty into the research or problem. For that, first of all, you need to understand how these systems work. Okay. One of such approaches is optimization. Let me take an example. You have developed, for example, a stock market. We have bought one stock from one company, let's say Reliance. That stock is changing continuously from its face value is continuously changing from one day to the next day or in a week or in a month, in a year. So we have 6 months data. Now, you want to take a decision whether you want to sell that one or you want to keep it with you. For that, you need to know how it performs in the next 1 month. Depending on that, if the trend is going up, then you do not want to sell. If the trend is saturated, or if you feel that it is going to go down, then obviously you will be selling it. Right? So now we want to know who will tell us how it performs in the next 1 month or next 1 week. What is going to happen to this stock? Who is going to tell us? For that, you need to develop a model. So this model needs some data. Already we have some 6 months data. We have the 6 months data now, and we want to develop a model. Right. So this is what is there in our hand now. Now we want to develop a model. But how to develop? We do not know. So for that, we need to have a domain knowledge first. First point is we need to have a domain knowledge. For example, if I go to Germany, I will not be able to speak the German language because I do not know. I do not have the domain knowledge. And how to behave in Germany, that also I do not know because I did not spend much time in Germany. So I do not know the surroundings. I do not know how to talk to them. I do not know their language. So basically, I do not have the domain knowledge. So if you want to develop a model for prediction of stocks, you need to have the domain knowledge first. Once you have the domain knowledge, and then you can take this data available and you can club together and then develop someone has sent a message that whether I have shared the screen or not. No, I'm not presenting any slides. Hence, I did not share. Whenever I start writing something, then I can share my screen. All right? Yeah. Yes, someone is asking what is domain knowledge. Okay. For example, I'm working on my fields of interest, or one of my fields of interest is machine tools. So I need to have the basics of machine tools, right? What are the different types of machine tools? Lathes, milling machine, drilling machines, and unconventional machine tools, EDM, like water jet machine or lasers, laser machine tools. So like there are different types of machine tools. And then what is the principle of working each machine tool? And then what is the principle of each machining process? Not only machine tool, machining process. Which machine tool should be used for which machining process? And then if I want to cut hard materials, which machine tool I need to use? What is the cost of the machine tool? So this is the domain knowledge. Suddenly, if you ask me related to finance, I will not be able to answer because that's not my domain. So hence, I do not have that domain knowledge. If you ask me about computer science or cyber security, I will not be able to answer your questions because I do not have the domain knowledge. I hope it is clear. So basically, you need to have the basic understanding of that field in which you want to develop models. That is the domain knowledge. So why you need to have the domain knowledge? Because AI and ML, you should not misunderstand that those are magic boxes. Those are not magic we see in circus, right? So it will not the magician suddenly he brings some bird from nowhere. So that is magic trick. That is a trick. So such tricks are not, AI and ML are not such tricks. They are properly developed systems and properly developed models. As I said, if you want to hack some computer, you need to know how it works. In a similar way, there are proper algorithms, proper systems, proper mechanisms to develop AI and ML. So it is not a magic box. That is what I want to stress here. That means you have proper algorithms and flowcharts to develop these machine learning and AI algorithms. Right. Good. Now, let us go back to our discussion. We have data in our hand for 6 months stock market values for that specific stock. And then we have the domain knowledge of the stock market. You know these two things. Now, we are going to develop the model. Right? Now, let me share my screen. Yeah. Could you see the blank PowerPoint screen? Okay. I have already shared it. Maybe in a moment you should be able to see.
Yes, now it's visible.
Yeah. It's a white screen. There's nothing on that.
Yes.
Right. So now you have data. Data, that means stock value, let's say in X and Y. y is the output, and then x is the input. So you have some data. Now you want to build this is the data. Now you want to build a model for this. That means y equal to function of x. You want to build this model so that tomorrow, if you get a new input, you can get this output, corresponding output. But what is this f of x? It can be a linear function, non-linear function, or exponential function, or something with trigonometric things, sin x, cos x, tan x. But we do not know. So that is the reason you need to have the domain knowledge. If you have the domain knowledge, then you can say it increases, x increases with y in a linear fashion, or in a quadratic fashion, or in an exponential fashion. Right? If you know this is x and this is y, if you know this domain knowledge, then we know what is this f. So let's say I will write x power n, k multiplied by x power n, y equal to k multiplied by x power n. That means I am saying that if you keep changing the x, y will vary as a function of x in an exponent manner. It is like x power n. N is an exponent. So this is called domain knowledge. Right? How it is, we are trying to put this behavior in mathematical form. If you know that, then you have these values. One value for x, corresponding y value, another x, corresponding y value, another x, corresponding y, another x, corresponding y, another x, and corresponding y. These values you have, right? So now, I want the values of, I want to find out k and n. If I know the k and n, I have developed the model. I can develop, if k is 2 multiplied by x power n, if it is 5, yes, so y equal to 2x power 5. That is the model. Now, if you give me a new x, I will substitute here, and then I'll get the y value. So you can see that there is no magic. There is an equation. So this equation goes into the, whatever you say, neural networks or fuzzy logic or genetic algorithms or deep learning or CNN or random forest or ensemble averages, whatever it is. In all those models, there will be such equation will be there inside, and then this equation will take different values and predicts the output. Okay. Now the question is, how do I get this 2 and 5? How do I get? In order to get these values, I use this data. Okay. In our 6th standard and 7th standard, we have seen some 2x plus 3y equal to 5, and then 5x plus 4y equal to 2. I want to know what is x and y. You know how to do this because it is very simple. 2 equations and 2 unknowns. So it is very easy. You get x and then substitute this x in this equation, and then you get the answer y. And then, for example, you get x. How do you get x here? X equal to 2 minus 4y by 5. So this x you substitute here, right? So now this whole equation is in y. So you get y value, y equal to so and so number, numeric value. That numeric value you substitute here. So then 2 minus 4 multiplied by that numeric value by 5. You get x. So you got x and y. Right? As simple as that. This we have studied in our 6th standard and 7th standard. Now the question is, you have two unknowns and you have many equations. So each data point is an equation. So for example, this y plus this much x equal to so and so, or so and so multiplied by x equal to so and so y. This x equal to this y. This x equal to this. That means you have more equations than unknowns. Unknowns are only two unknowns, but these many equations. So you cannot solve in this way. Then we go for least squares method. Least squares method. What do we do in least squares method? Whatever the y value, we take that y value, that is y actual, minus y predicted. Predicted means for this is the domain knowledge. In this domain knowledge, we substitute this x. If you substitute this x, then you get y predicted. That is y predicted, right? And we will square it. Why we will square it, I'll explain you later. This is for point 1. Similarly, we do it for point 2. Similarly, point 3. So that means for I equal to 1 to how many? 5 points. For 5 points, we do this and add, and we try to reduce that error. Okay? If you try to reduce that error, then we get these values k and n. Okay? So we randomly select k and n initially. We randomly select k and n and then try to substitute that here, and then we get y predicted. That y predicted is this one, but corresponding y value is this one. If whatever the k and n that you had selected, if they are the right numbers, they are the real correct numbers, then this error would be 0. Is this point clear? Because this is very important in machine learning.
Sir, can you please explain again?
Yeah, I'll explain. This is very, very important in whole machine learning approaches. Okay. See, this is the domain knowledge. Yes. So this is the domain knowledge. That means we know that how it behaves. If you increase the x value, how y value changes. That is the domain knowledge. But we do not know exactly. We know that if you increase x, y increases. That much only we know. We do not know the actual numbers. At what rate it is increasing, we do not know. That means this k and n, we do not know. But we know that it is x power n. That n value we do not know. Our basic idea is to know this k and n from this data. That is the basic idea. Now, how do we do? We want k and n, but we do not know. But only thing is we have this data we have in our hand. Now what we will do is we need to select somehow this k and n in such a way that the error should be 0. Or the other way, if you select correct k and n and substitute this x value here, whatever the y predicted you get, it would be this value. Is it clear? This point is clear.
Yes, sir.
So I'm repeating once again. For this x value, you have this y value. Okay. Now, let us keep this y value here. Now you substitute this x here. And then if k and n are correct values, then this whole will be giving yp predicted. This y predicted will be equal to this one. So everything depends on the k value and n value. If they are correct values, then by just simply substituting this x in the domain knowledge, whatever the predicted value that you are getting, it would be the actual value. Similarly, if you substitute this x here, if k and n are correct values, then whatever the yp you are getting, that would be equal to this one. That means the error between this and this would be 0 because both are same. So that is what I'm saying here. In this equation, what I'm saying is y actual value, that means this value, minus y predicted value, that means this value. Both will be the error, the difference should be minimum. That means this should be minimum. That means error, by substituting this x, you get this. So the difference between this and this plus the difference between this and when you substitute this x, you will get another y value, this and this. So the sigma means it is summation of this error, this error, this error, this error, this error. Total error should be minimum. Okay, that is the least squares method. That means when you are squaring it, the error should be minimum. Y square, because let's say this is the trend line, right? This is the actual values of y. But when you are predicting, you might get predicted value corresponding to this here, corresponding to this here, corresponding to this here, corresponding to this one. So all these black dots are predicted values. All the red points, whatever are there on the red curve, those are these points. So some points are above, that means positive error. Some points are below, that means difference is negative, positive, negative. But we do not want to worry about the sign. We only need to reduce the difference between predicted and actual values. Okay, so that is the reason we are squaring it. Even if it is negative, it will be positive. If it is positive, again positive. So for all these points, this much error, this is this much error, this much error, this much error, let's say this much error, say this much error. So I want to reduce the summation of all these errors. Okay, so what am I going to get? I'm going to get k and n values in such a way that at all these points, the error will be minimum. Okay, now once again, I'm repeating. So in the I want to find out k and n values in such a way that the error between actual value and predicted value is minimum, so that those k and n values, when I substitute any of these x-axis, they will give minimum error. Okay, this is called optimization problem. Optimization problem. Now I hope you understood how machine learning and AI is related to optimization. Okay. Till this point, any questions?
Sir, one small question.
Yeah.
Sir, you selected the relation between y and x. It's like y equal to k into x power n, some direct polynomial equation.
Yes.
And we taken the sample data and try to evaluate k and n by using uh, again using minimization method and made the final equation.
Yes.
But if by mistakenly, if for example the relation between y and x, like y is equal to k into x power n plus some next k2 into x power n minus 1 plus some so on.
Yes.
So if by mistakenly if I take the assumption of the equation, and then we may miss the next terms, we may miss the next terms, like
Definitely.
k2 into n x power n minus 1,
Definitely.
those items.
We will be missing
So
it. We will be missing it.
then how to select a general equation? Can we have any general equation, or what is the methodology to select this polynomial equation with respect to number of that constant values?
Yes. Yes.
And
It is
could you please
it's a very good question, because it is very much relevant to what I'm trying to explain. So the idea is here, just for the sake of simplification, I have taken only one term, just for the to make the example simple. I've taken a only one x. But in general, we take a long polynomial, so that we take more than what we want. That's why if you see and open the neural networks equations, you will get very lengthy polynomials,
okay,
right? So there is a problem with that. What will happen is it will tries to overfit.
okay.
What is the meaning of overfit? Let's say I have data like this. Yeah. So one more data is there, one outlier is there here, and somewhere here. Yeah. Now, so this is X and this is Y. Now, so visually we can see that again here dimensionality comes into picture. I'll explain you what is dimensionality, but at present I have taken only one-dimensional data, because one independent variables. All the terminology let us introduce at later stage. Now we have two possibilities. One, connecting all the dots. Is it better, or this is better? Which one you feel more comfortable?
Green colors.
Absolutely, right?
Yes.
Green color looks more meaningful, although it is giving error in multiple places, but it has captured the behavior of the system.
Yes.
That is called generalization.
Okay.
Generalization. Whereas red one is called overfitting. Red one is called overfitting.
Okay.
So green one is called generalization. We always expect generalization from the any algorithm or any model. But why did overfitting happen? Because we have increased the terms in the polynomial. N1, N2, N3, like this. N3, this is N1, like this many. As you increase the number of terms, the flexibility of the curve increases. For example, even power or number of terms, when you increase, the flexibility of the line or curve increases.
Yes.
So that is another danger by using more and more terms. But
Okay.
neural networks inherently has this feature of, because you will be using multiple hidden layers, multiple hidden nodes, even in fuzzy logic also, you will have multiple membership functions, multiple shapes, even random forests. You will have multiple connectivities, multiple trees, and it is like this in random trees. So as you have more and more cases, the flexibility of the equation increases. The moment flexibility increases, it tries to go through all the points.
Okay.
These points might be outliers. But however, there might be some experimental error. When you collect the data, there might be some errors. So, but when this higher order polynomial have more flexibility, hence it tries to go through those points. Then you can ask, what is the problem in going through all the points? Because you will be
Maybe errors may be incorporate.
exactly, you will be losing the generalization capability.
Ah.
And then if I ask this point here, what is the value of y, it will go and give this. Whereas this is the more meaningful value, but this will give this value.
Yes.
And again, here if I ask some value, or here if I ask something, it will give this. Whereas the actual value is more nearer to this blue curve. So that is the issue with giving more flexibility. Right.
Okay.
So you need to strike a balance between these two. If you don't increase the number of terms, it might not be able to capture complex phenomena.
Okay.
Whereas if you increase the terms, then it might overfit. So it is like a balance between these two things. That is where multi-objective optimization comes into picture.
Okay.
Are there any messages?
Sir, in simple terms, what is actual and predicted value definition in simple terms?
Sorry, I could not understand. Can you please repeat?
In simple terms, how we can define actual value and predicted value?
Okay.
Definition, sir.
Okay. Sure. Actual value and predicted value. See, a model in class, most of the times I give this example. Ramp walk modeling happens on ramps. The clothes they display, right? In modeling. Do you get this example? Ramp walk.
Yes, sir.
So in ramp walk,
Yes, sir.
models, they wear different dresses and walk. What is the purpose of it? They want to show us if someone wears this dress, how they look. Right? If someone uses this product, how they look. That is what the basic idea of modeling on ramp walk. Right? If you wear these winter clothes, how you look. If you wear the summer clothes, how you look. That is what the basic idea. That is the ideal case. But in reality, when we wear, how we look, that is the predicted value, right? There is a mismatch between the ideal case and the predicted case. It is just in a lighter sense, this example. So that is, but this is a very, very good example for understanding modeling. The other thing, you have a machining process, for example, some unconventional machining process. When you have done an experiment, you will get the actual value. When you did an experiment, you will get an actual value. But whereas you develop a model, when you develop a model, you will not consider all the parameters which are affecting the output. You will only consider a handful of parameters and develop a model. So this model will not be able to predict will not be able to tell you the actual value correctly, because you have not considered all the parameters which are affecting the output. So this model can only give you a near value, that is called a predicted value. Let me explain you a little bit clearer way. We have a process. This is the process. This is the machining process. This machining process is influenced by, let's say, 5 parameters, 5 input parameters. And we are getting an output, right? If you consider output as a function of x1, x2, x3, x4, and x5, this is the ideal case. So this one, you get actual value, output actual. But whereas I do not know that all the 5 parameters are influencing the process, with my limited knowledge, I only come to know that this and this are influencing. Then what will happen? Output equal to function of, I know that only x1 and x2 are influencing the process, right? So I will get from this is the model. This is the actual process. When I use this model with my limited understanding, I will get output predicted. So this is called predicted, because I'm trying to predict. I'm trying to predict what would be the output if I give so and so input. But the reality is, it is influenced by these many parameters. This is the reality. If I know this, then only I will be getting actual output. Whereas with my limited understanding, I developed a model without having much understanding about the process. So when I use this model, whatever the output that I get, that is called predicted output. Could I make your doubt clear?
That means if we consider all the variables, then it is called actual, and if we consider some variable, it is called predicted.
Yes. But
Okay.
actual is not always possible, because this is the ideal case. Each process is influenced by, let's say, 100 parameters. And first of all, you do not know all those parameters. So only thing is, we do experiment and then get that value. Even while doing experiment also, you might not be able to consider all these parameters. For example, you want to cut a diamond. So you cannot do 100 experiments on diamond. It is too expensive. That is one thing. Second, you might not know the basic physics of the process. You might not. This is F. F is nothing but physics. Basic physics of the process. Although you know x1, x2, x3, x4, x5 are influencing the process, but you do not know how they are influencing the process. Hence, what you will do is you will conduct an experiment. So experiment, we have to believe. When you do experiment, all these process parameters will be influencing the output, and whatever the output that you are getting, that is the actual output. But when you develop a model, you do not know the physics, but you have a minimum understanding about the physics. So you will be thinking that x1 power n1 plus x2 power n2. But this physics might not be right, or this physics is only a partial physics about the process. You do not have complete understanding about the process. But when you do experiment, whether you understand or not, all the physics will be applied. And then you get the output. So that is the reason we call it as actual output. Whereas here, you are not very sure about the physics, and you are not very sure about how many process parameters are influenced. That means your understanding is very limited. With that limited understanding, you are trying to get output. So this is called predicted.
XL may be called practical experimental result, and
Experimental or
predicted means
actual, all are
theoretical.
same. All are same. Experimental, actual, all are same.
Okay, and predicted means theoretical.
It's we should not say, yeah, in one way you can say theoretical, but a better wording is your understanding.
Okay.
Your understanding. Because tomorrow your understanding will change. If you read another paper or another textbook, your understanding will change. Then you
Okay,
will
in
develop.
In simple terms, we can say in XL we consider all the variables, in predicted we consider not all the variables.
It's not actual, and you don't consider all the variables. You conduct an experiment. Experiment will always be influenced by all the parameters.
Okay.
First of all, you don't know all the parameters, right? If you know all these parameters, here itself you will consider all of them. You do not know all these parameters. But when you conduct an experiment, all these parameters automatically will take place, their role in the experiment.
Okay.
So that is the reason we call it as an actual. Whereas with your limited understanding, you consider a limited set of parameters and limited physics, and you try to predict this, and from that, whatever the output that you get, that is called predicted value.
Sir, can we consider like experimental values like to find out the general equation? After that, we have only x value, but we want to predict some values, so that we are using that already generated general equation or that algorithm, and we are predicting the next values to get the output. Is it necessary?
Yes, absolutely. You form a generalized equation, and then you try to find out those exponents and constants from the experimental data, what we have done in the first slide.
Yes, sir. Then we are going to use that for our purpose. That is what.
Yeah, for your future applications.
So we are going to use it.
Yes, absolutely.
So since we minimized all these errors, all those things, it will try to give the more better values. If at all, if we feel that next also any variations is there, we will try to use some other algorithm or some improvement in the existing equation, so that we can improve is it, sir?
Yes, absolutely. But you need to remember one point, that this is only approximation.
Okay, sir.
You will never be able to reach to the actual.
Okay, actual value.
Actual behavior. This process behavior, we will never be able to reach.
Okay, sir.
It is very similar to the ramp walk. And ramp
Okay.
walk, whatever they are doing, whatever you do, you will never be able to look like them.
Yes, sir. We will never be look like them.
Right. So it
Yes.
is very similar to that. So
Yes,
in a
sir.
similar way, this model, you will never be able to reach to the
Ah,
actual model because
okay.
that is influenced by multiple parameters.
Okay, sir.
And then physics, multiple physics will be involved.
Okay.
So for example, you take a cantilever beam
Yes, sir.
and then try to apply some load on it.
Okay.
And you will be thinking that whatever the deflection that we had got,
Ah.
it is only due to the load that I applied.
Oh, yes. But
But
it,
outside temperature might be different. That temperature will soften the material,
oh, yes, yes.
right? And then
Environmental conditions.
exactly. After that, a very high wind might be a gush of wind might be
Okay,
flowing onto that cantilever.
okay,
That takes away whatever the heat that is there on the cantilever.
okay, sir.
So multiple physics are happening there. Heat transfer is happening, fluid mechanics is happening, and
Okay.
then structural mechanics is happening. But
Okay.
whereas we are only considering structural mechanics.
Yes, sir.
To
Because it's a major values, major
exactly,
parameters.
exactly. In models, generally, what do we do is significantly affecting physics, significantly affecting process parameters, we consider.
Okay, sir.
Remaining things we neglect.
Yes,
But it doesn't mean that remaining things are not influencing.
yes,
As you are not considering remaining things, that error will be there always.
yes, sir.
Okay?
Yes, sir. Understood, sir. Thank you.
Sir, because of doubt, sir, because of this only they are going for artificial neural network, sir, in order to develop that this multi-dimensional equations.
Yes. Artificial intelligence we are using to reduce these errors, to capture the complex, what we say, the complex
Equation.
physics. So
Thank
this physics, whatever is there, which we do not know, or
Yes.
we might have understood only 60% of the physics or 70% of the physics.
Yes.
Remaining 30%, we
Because
might
of
not.
the experiment data, only 70% is we can.
Yes. Those things, these artificial intelligence approaches will try to capture in a better way from the data.
Okay, sir.
Because the equations are complex equations that we are going to use in neural networks and fuzzy logics. It is like very similar to increasing the order of the polynomial.
Yes, sir. Thank you.
Yeah. So shall I go ahead?
Yes, sir.
Yes. Now, okay. I would like to give some basics about the optimization. Optimization always have an objective function that is minimization of function x1, x2, x3. Let's say only 3 variables. This can be minimum or maximum or exact value. That is called nominal. So these are the 3 cases you find in optimization. What is minimum? For example, I want to minimize the cost of the equipment. That is minimization problem. I'm making a product. I want to reduce the cost of the product, which is a function of multiple things: material, weight, technology, or multiple things. So by considering all those parameters, I want to minimize the cost of the product. Okay. Second, what is the example for maximization? I want to maximize the profit or nominal. This is very important. What is nominal? I do not want to minimize, I do not want to maximize. I want to get exact value. For example, I want to turn, all of you know turning. I hope all of you know turning. So we want to turn a component exactly to 100 millimeters or 50 millimeters. I do not want more than 50, or I do not want less than 50. I don't accept 49. I don't accept 51 because the whole diameter is only 50. The whole diameter is 50. So hence the shaft also should be 50 only I need. I do not want bigger or smaller. Right. If I want to assemble these two things in an assembly, I want exactly whatever the hole diameter, that much shaft I need. That's it. I don't want to maximize or minimize. So that is nominal. So basically 3 optimization cases: minimization, maximization, and nominal. So, and then this is called objective function or cost function. After that, these are the design variables: x1, x2, and x3. These are called design variables. x1, it has a lower value, x1 lower, x1 upper value, x2 lower value, x2 upper value, x3 lower value, x3 upper value. What is the meaning of it? I want to minimize this function in such a way that x1, x2, x3 can vary between this, and this. x1 can vary between lower and upper, x2 can vary lower and upper, x3 can vary with lower and upper. So in these limits, I can vary x1 and x2 and x3 and find out suitable x1 and x2 and x3 in such a way that this function is minimized. This is the definition of single objective optimization. In order to solve this problem, we have hundreds and hundreds of algorithms. In fact, thousands of algorithms, right? Here we are only using single function. That is why we call it as single objective optimization. If you use multiple functions like f of x1, x2, x3, that is f1 of, and then f2 of x1, x2, x3, and f3 of x1 and x2 and x3, whereas x1 varies between these limits, x2 varies these limits, x3 varies these limits, right? I want to minimize f1, maximize f2, minimize f3 by varying the x1, x2, x3 in these limits. So you are trying to play with multiple objective functions, then it is called multi-objective optimization. Okay, this is single objective optimization. This is multi-objective optimization. Right. So now let me give you an example for multi-objective optimization. If you see the air traffic, aircraft, so air traffic, if you see any big junction like Frankfurt in Germany, so thousands and thousands of flights keep coming and going to the Frankfurt airport, right? So now, have you ever imagined who plans all these things? Which flight has to come and from where and what time it can stay, how much time it can stay, and how many flights will be leaving from the same airport. It is impossible for a human being to handle those many flights. And also it is not as simple as planning them. Some flight is supposed to come today and then it will be delayed by 1 hour. Some flight will come 1 hour early or 10 minutes early. Some flight will get delayed by 1 day, right? It is not very simple activity. So they don't listen exactly what you are saying due to weather conditions, due to political conditions, due to multiple reasons. the functionality, some repairs, due to all these things. You need to consider all these things, right? So that is the reason flight ticket costs are a little bit expensive. Why? Because they need to take so much of so much care and so much redundancy they need to take. For example, what is the surety that all the flight seats will be filled on one day? There is no surety. So what is the surety that all the flight seats will be filled today? And tomorrow you might be overbooked. There might not be any seats. If you don't provide seat to a customer, you will be losing money. Whereas if you go without filling all the seats, again you lose money. So that means you can see that there are multiple things that you need to take care. There is no single function that you can optimize, that you need to optimize. There are multiple functions you need to optimize. Okay. So that is the reason multi-objective optimization is very, very, very important. Right? Right. Yes. Now let me give a simple example. I want to buy a car. Okay. I want to buy a car, a four-wheeler car. First, on this, I take cost, and then fuel efficiency. Or instead of cost, let me take cost, fuel, and then fuel efficiency, and then comfort. Okay. You can see the military equipments, they are not designed for fuel efficiency. They are designed for doing the task. It need not be fuel efficient. Whereas the luxury cars, they are also not designed for fuel efficiency. Right? They are designed for comfort. Right? The moment you try to take any BMW or Audi or Ferrari, so those are all comfort, right? So when comfort increases, fuel efficiency decreases. When comfort increases, fuel efficiency decreases. When fuel efficiency increases, comfort decreases. So both are contradictory in nature. If you try to increase fuel efficiency, then comfort goes down. If you try to increase the comfort, then fuel efficiency comes down. Right? These two things do not go hand in hand. All right. So that means if you take point here, this is, you might get 100% fuel efficiency, but 0% comfort. Here, if you take this point, you get very low fuel efficiency, but very good comfort. Okay. So, but here, if you see, take this, and here, if you take this, and here, if you take this, there will be a compromise, right? You lose some fuel efficiency, you gain some comfort. Or if you go the opposite direction, you lose some comfort and you gain some fuel efficiency. That means each and every point on this curve has a point. We cannot discard any point by just saying that this is not suitable, because that is the reason this front is called Pareto front. Okay, so what it means, you take this rectangle and there are multiple points. Each point is related to comfort and fuel efficiency, right? So, but if you take this point and this point, or this point and this point, so these points which are marked, and then points on the front, Pareto front, you can see that Pareto front points are better points than the marked points, right? So why? Because here there is a concept called domination. What is domination? Domination means better points. The points which are there on the Pareto front, they are better than the outside points. Okay, that means they have better fuel efficiency and better comfort. But now the big question is, how do we find this Pareto front, which has all the better points than other points in the space? How do we find out? That is where multi-object optimization comes into picture. And let me give an example related to, I heard that all of you have spent so much time in listening to neural networks. So in neural networks, in designing the neural networks, what is this design of neural networks? Identifying how many layers and how many nodes in each layer. That is a design problem, right? If you increase more nodes, computational complexity increases, but you get the flexibility. But if you decrease the number of nodes, computation complexity decreases, but capability of flexibility to capture the nonlinearity in the data reduces. That means we need to, these two are two contradictory, very similar to this problem, fuel efficiency and comfort. So number of nodes and computational complexity, these two are contradictory in nature. Okay, so that is again a multi-object optimization problem. So in order to design neural networks, you need to understand multi-object optimization. Okay, so yeah, let us go back again. So you, instead of optimizing only one function, instead of trying to optimize only one function, we are trying to optimize multiple functions. Again, multiple functions you are trying to optimize, but how? I'll tell you two options. First, I will, so in this space, I optimize function 1. I get this area. Then in this area, I optimize function 2. Then I get this area. This is the optimized area. In that area, I optimize function 3. Okay. This is very it looks very intuitive, but it is a wrong approach, because when you are trying to optimize simultaneously, then only you will be able to explore the nonlinearity. Wherever F2 is maximum, that area might have, for example, let's say this is the whole area, and this in this area, F2 might be maximum. But what did you do? While trying to optimize F1, you have eliminated this area. You are only left out with this left part. But in this left part, you are trying to see optimize F2. So all of you got the point here. This is the whole area wherein, let's say, in this hatched area, F2 has maximum value. But what happened? But this area got eliminated. While F1 is getting optimized, this area got eliminated. So only this area is left out for F2 and F3. Whereas F2 is maximum in this area. But however, F2 is not getting opportunity to explore this area because this area was eliminated by F1. Now only this area is left out, in which F2 will get second minimum. Right? So hence, optimizing functions one after the other will not be able to find the actual optimal. So hence, what do you need to do? You need to do simultaneous optimization. That means you take one point in the whole space and then try to optimize all the F1, F2, F3s. Take another point and try to optimize F1, F2, F3, and then compare them. Whichever is better optimizing F1, F2, F3, select that point. That is the right approach. Okay. So that is multi-objective optimization simultaneously. So basically what we get a Pareto front finally. Right. So there is another approach. You might say, I will consider F1, F2, F3, but I multiply with A3, A2, A1, and then do the summation, and this is F. Now I try to so multi-objective optimization, you convert it into a single objective optimization. Then you can use this approach, right? But there is a problem with it. How do you select A1, A2, A3? That is the question. Okay. If you randomly select A1, A2, A3, then you get 1 point on this Pareto front. If you select another A1, A2, A3, you get another point on this Pareto front. If you get another A1, A2, A3, you get this Pareto front. Right. So basically what is happening? By converting multi-object optimization into single object optimization, you are only able to get 1 point on the Pareto front. You are not able to get the whole Pareto front. If you want to get whole Pareto front, whatever I explained previously, so you need to consider all F1, F2, F3 simultaneously. That means at the same time. You need to consider them, and then you need to evaluate the objective functions. Then only you will get the whole Pareto front. So are there any questions? Yes. So till this point, are there any questions?
No, sir.
Sir, Pareto line is the line which optimizes all the three functions.
All the three functions. Yeah. Basically, what happens is you have, let us take only two functions, F1 and F2. It is easy to explain. F1 and F2. And then you have multiple points. And by the way, I did not explain, this is called objective space. Objective space. And there is another space that is parameter space. This is X1 and this is X2. This is parameter space. Right? So F1 of X1 comma X2. F2 of X1 comma X2. If you substitute all these points, for example, this point, take X1, so and so X1, so and so X2. If you substitute that in F1, you get one. If you substitute another point, F1, F2, you get another. So F2 of so much, F1 of so much, this. For this X1 and X2, this X1, this X2, you take this X1 and X2, substitute in F1 and substitute in F2, both will meet here. Similarly, you take another X1, X2, this point, substitute in F1, substitute in F2, you get another point. Again, take another point, X1, X2, substitute in F1, substitute in F2. Both, if you plot, you might get this. So like this, all these points you get corresponding to all these X1 and X2. Is it clear?
Basically, intersection of F2 and F1.
Yes. F1 and F2 intersection is one point. That is why we call it as objective space.
Okay.
The other one is parameter space. Okay?
Sir, is this like if it is average voltage milling, I should get maximum milling depth and the minimum surface roughness. In that
Exactly.
case, what is the input parameters I should select so that I can get in both the way? That is.
These are the input parameters. For example, pressure
X1, X2,
and mass flow rate. These are the input parameters.
Okay.
So this combination, if you substitute in F1 and F2, their intersection will give this value.
Okay, so that gives minimum roughness and maximum milling depth.
Till now, we are not doing any minimization, maximization. Only thing is, these values, if you substitute in F1 and F2, corresponding points, we get throughout this box.
Okay.
Now, our aim is to find out the Pareto friend. Let's say, Pareto friend is somewhere here, but we do not know how to go there. We were only given these black dots because we know all the X1, X2 points. If you substitute correspondingly, if you take intersection of F1, F2s by substituting them, you get these points. Now we want to find out the Pareto friend. For that, there are different algorithms. There are like NSGA, NSGA1, NSGA2, NSGA3, and then weighted optimization, what we have discussed, and PGSL, and vector multi-object optimization, or multiple methods are there. Even goal programming is also for this. So let us not, we don't have time or much time to discuss about these algorithms, but what these algorithms does is they take these X1 and X2 values and tries to find out the points on the Pareto front. Okay, there are two conditions. One is all the points should get distributed on the Pareto front in a more uniform fashion. At the same time, it should go towards this corner. Okay, Pareto front, it might start like this, this. Finally, it should go here. At the same time, the spread should be uniform. Those are the two conditions these algorithms should follow in generating the Pareto front. For this purpose, we use genetic algorithms, because genetic algorithms can find is a population-based approach. It can work in parallel. So let me give some introduction to a little bit more about optimization. Let's say this is the error surface. Now I want to find out minimum of this one. I want to find out the minimum of this. Right? Visually, you can see here. Hence, you can immediately say, yeah, this is the minimum. What is great in that? But it is only one variable, x1. Now you take x1 and x2 and x3, right? And y. That means y is a function of x1, x2, x3. Right? Now you get a complex surface. So very complex surface. Now, first of all, you can't visualize. If number of parameters increases, these are called independent parameters. This is dependent parameter. As number of parameter increases, the surface will become high dimensional. Once it becomes high dimensional, you will not be able to see. Right? So, but for discussion sake, we are making this only one parameter we are taking. So here the actual minimum, but let us say we do not know where this is. Right? So what we will do is we take one point xn plus 1 equal to xn plus delta x. First, xn, at this instance, we take randomly one point and we add some value, and then that is the next point. We add some value and we got here. Third time, we add another value, we went there. Or next time here, next time here, next time here, next time here. Finally, we come here. Okay, this is the basic rule. We take one value and add something else, then we get the new value. Once you get the new value, you evaluate function value at that point. First is xn, n. The next is this is xn plus 1. So xn plus 1, you evaluate function value. And then compare previous function value and present function value. Right? And then you also see the slope here. When slope is, so the basic logic is, yeah, basic logic is here, if you see, slope is 0. Whereas slope coming and decreasing, 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 and then finally 0. So, you know f here and f here. So when you know two values, you can find out the slope. And again, this will become xn, this will become xn plus 1, next stage. So you know two f values. Again, you find out the slope. Now you see when slope starts decreasing, then you are going in right direction. You keep continuing this and evaluate f values. So this whole process will be continued till the slope becomes 0. Once slope becomes 0, then you can blindly say that you have reached the minimum point. Okay? So this is the way optimization works. But now, let us say this is the error curve. Then you take slope here and here decreasing, decreasing, decreasing. Finally, it is 0. Right? But that is not the minimum. This is the minimum. But our rule says wherever slope is 0, that is the minimum. But so you are misled. So this is the here also 0, but here also 0. But as here you got 0, you will not move in this direction. You don't get chance to explore this. Because already it is 0. You will be thinking that that is the maximum because you cannot visually see this. Visually see this curve. Hence, you will be thinking that, yeah, I got slope 0, so this is 0. So, then this is the problem with conventional single objective optimization approaches. Conventional. Now, unconventional approaches have come, like genetic algorithms, particle swarm optimization, probabilistic approaches. Yeah, so this sort of things. What do they do? In genetic algorithms is a population-based approach. What do we do? Instead of starting at one point, we take multiple points and then start with all the points and then compare whichever is better, right? Like this, again, improve those points, again, start multiple points, again. So this keeps continuing. This keeps continuing, and then so that even this point gets stuck here, this point says goes here, or this point goes here. So you will not miss this area. But whereas if you start with only one point, it might get stuck here. Okay. So what we will do is we take multiple points and then start in parallel, so that you will not miss the global optimal. This is called local optimal. This is called global optimal. Okay. So genetic algorithms has multiple operators, that is crossover, mutation, and then selection. So all these operators make sure that always you go towards the global optimal. Even if you miss sometimes, the operators will make sure that you will not miss the global optimal. Okay, this is the single objective optimization. Same approach we use genetic algorithms. This is NSGA, non-dominated sorting genetic algorithms. With same genetic algorithms we use and try to explore multiple points on the Pareto front. Okay, so with this, I think we are touching. We have already crossed 9:15. So with this, I would like to. I was given 1.5 hours. Many more things are there to explain, but at this stage, I will stop. And I'm happy to answer any questions.
Sir.
Yes, please.
Sir, a diagram containing F2 and F1 function is called open space function. Open space diagram.
Which one?
This diagram, sir.
This one.
F2, no, sir. Next, previous one. Yes, sir. This figure on the left-hand side is representing O space. O space means?
No, objective space.
Objective space. Okay.
Yeah, objective space. This is parametric space.
Okay, okay.
Yeah, it is nothing. See, x1 and x2, when you vary them at different combinations, what f1, f2 you get. That's it.
Okay.
There's nothing great in there. Yeah. Any more questions? So already some standard softwares has come for designing of neural networks. Someone is asking multi-object automation and then neural networks. But the standard softwares have come. They have already implemented by using by designing neural networks using genetic algorithms. Yeah. If you want to read genetic algorithms, then you can get a book by Kalyanamay Dev, the genetic algorithms, and Kalyanamay Dev multi-object optimization. He is a pioneer in this field, so he has written these textbooks. So. Any more questions?
Dr. Srinivas,
Yes, Professor.
yeah,
Vikram.
any clarification from the audience?
So one was objective space, another was parametric space.
Parametric space, yes.
Okay.
So I think we'll conclude the session today. First of all, thank you very much, Dr. Srinivas, for giving your elaborate presentation on what is the formulation of the problem and how to solve the problem by using multi-object optimization. Thank you very much. Today we'll conclude the session, and tomorrow we have 2 more sessions, and by Professor Piyush from IIT Madras regarding the bearing health monitoring by using AML, and followed by AML application additive manufacturing. So thank you one and all. Good night to all.
Thank you all, and thank you,
Sir,
Professor Vikram.
book name, can you tell once? Book name?
Yeah.
This is multi-object optimization by Kalyanamay.
Kalyanamay.
Kalyan Vaidev, sir.
Yes.
Yes.
Okay.
Yeah.
Thank you, sir.
Once again, thank you, Dr. Srinivas.
Thank you, Professor Vikram. Thank you all. Good luck for all your research. Thank you. Bye-bye. Good night.
Thank you, sir.
So, shall I log off? Yeah. Thank you. Bye-bye.
Sir, please send me the feedback form.
Sorry, do I need to fill? Okay. Yeah. Bye-bye. Good night.